The topic is finding gradient vectors and directional derivatives. So let's do the first example. Let f of xy equal x cubed y plus y. Question A, find the gradient of f. Now, by looking at the definition, the gradient of f is partial of f with respect to x times I plus partial of f with respect to y times j. We can even use the other notation. This will be fx, fy, the vector. Right? Alright, so in other words, all we need to do find f sub x and f sub y. Alright, partial f with respect to x of any xy is going to be equal what? We take in partial derivative with respect to x, so y is a constant we don't touch, so it's 3x squared y, constant we don't touch it, plus partial with respect to x of y is just 0, so that's it. What is f? Partial derivative of f with respect to y of any point xy. Same thing. Now y is supposed to be the variable and x is a constant, so x cubed is a constant we don't touch, so this is going to be x cubed, right, plus partial derivative with respect to y of y is 1, so therefore the gradient of f at any xy is equal the vector 3x squared y x cubed plus 1, right? If you like the other notation, 3x squared y times I plus x cubed plus 1 times j. So this is gradient of f at any xy. Now find the gradient of f at negative 1 and 2. Now we're going to use this definition. A and B means it's a given point, so all you need to do is plug it into the gradient of f. And so all we need to do is find fx of negative 1, 2, which means plug negative 1 into x and then plug 2 into y, right? Plug 1 here, plug 2. So this is going to be equal 3 times negative 1 squared times 2, and that's just 3 times 2 is 6, and then same thing, partial derivative with respect to y of negative 1, 2. Now we need to plug the x here, there is no y, so all I need to do plug negative 1 there, so negative 1 cubed plus 1, negative 1 plus 1 is 0. Now this means that the gradient f at negative 1, 2 is equal the vector 6, 0, or just 6i. Alright, now we need to find the directional derivative of f at the same point but in this direction. And by the way, just the reason why I'm using the u, the vector u is a unit vector. I mean, you can even check it. Norm of u is equal to 1 over square root of 2 squared plus 1 over square root of 2 squared, which is 1 over 2 plus 1 over 2, which is 1. So that's right. So now all I have to do is use the dot product. So gradient f at negative 1, 2 in the direction, f, I don't need this. Directional derivative in the direction of u at negative 1, 2 is equal gradient of f at negative 1, 2 dot the u. Now this is meaning we got 6, 0, so the vector 6, 0 dot the vector 1 over square root of 2, 1 over square root of 2. It's going to be equal 6 times dot product, 6 times 1 over square root of 2 plus 0 times 1 over square root of 2. And this goes to 0, so the answer will be 6 over square root of 2. If you don't like square root of 2 in the denominator, so it will be 6 square root of 2 square root of 2 square root of 2. 6 divided by 2 is 3, so that would be 3 square root of 2. Alright, now let's move on to the next example. Same question. F of xy equal y squared e4x. Find the gradient of f. Again, I need to find partial derivative with respect to x of xy, which is equal, now remember y squared is a constant I'm not going to touch, and partial derivative with respect to x of each of the 4x will be 4 times e4x, which is equal 4y squared e4x. Now same thing, partial derivative with respect to y of any xy. Now each of the 4x is a constant, so I don't touch, and then derivative of 2y, y squared is 2y, so this will be 2y e4x. This tells me that the gradient of f at any xy is going to be equal the vector 4y squared e4x and then 2y e4x. If you like the other notation, 4y squared e4x times I plus 2y e4x times j. Alright, now question B, find the gradient of f at 0, 2. So again, all I have to plug in is 0, 0 for x and a y for 2. So fx of 0, 2 is equal, plug in 2 for y, so it would be 2 squared, 4, I'm plugging it in, same thing like plugging it here, 4 times e, 4 times 0, each of the 0 is 1, 4 times 4 is 16. Now partial derivative of f with respect to y at 0, t, I'm going to plug a 2 here, so it'll be 2 times 2, and then I'm going to plug 0 for x, e 4 times 0, each of the 0 is 1, so this is 4. Therefore, gradient of f at 0, 2 is going to be equal to vector 16 and 4, or 16i plus 4j. Now question C, compute the directional derivative of f at 0t in the direction of v equal to negative 2. Now this time, this vector is not a u, it's not a unit vector. So, I mean, you can tell why, because norm of v is equal to 2 squared, which is 4, plus negative 2 squared, which is 4 square roots, not equal 1. So we need to find a unit vector in the same direction, and this is the formula. So my unit vector in the same direction will be v over norm of v. The formula you're supposed to memorize, which is the vector 2, negative 2. Norm of v is square root, like we said, 2 squared plus negative 2 squared, which is equal to 2 over square root of 4 plus 4 is 8, so square root of 8, negative 2, square root of 8. Right? Now we can find the directional derivative in the direction of u at the point 0, 2. We know by definition, and look at the definition right here, it's going to be the gradient of f dot u. So gradient of f at 0, 2 dot, so the dot product u, which means the gradient of f is right here, 16.4 dot the u, the vector u is right here, 2 over square root of 8, negative 2 over square root of 8. Now the dot product is going to be 16 times 2 over square root of 8 plus 4 times negative 2 over square root of 8 which is equal 32 over square root of 8 minus 8 over square root of 8. 32 minus 8, 24 over square root of 8. And we're done. That's it for these examples.